Okay. Um, we have the following example, and this is basically taken out of 9.3. I wasn't going to say much about 9.3. I'm just kind of harvesting an example out of 9.3. So 9.3 is about predator and prey models. So we talked about population models before, like the logistic model of growth. So this is, roughly speaking, kind of like that, except now there's two populations. There's the predators and the prey, and their growth rates interact with each other. So let's consider the following example. Let's say that X is the number of rabbits in millions and Y is the number of foxes in millions. Foxes do eat rabbits. I Googled it because I was doing this example, and then I was like, do foxes actually eat rabbits? But they do. So, right, we have the following system, and this is kind of just given to us, but let's talk a little bit about why this is a reasonable system. Of course, foxes eat rabbits, so if there's a lot of foxes, that's kind of bad for the rabbits, but if there's a lot of rabbits, that's kind of good for the foxes. So if the rabbits were left to their own devices without any foxes, then we're kind of assuming that it would just be exponential growth. Like if y were just 0, like if this thing in parentheses would just be 1, so I can just cover it up with my finger, I would get x prime equals x, which would give me, like, x would just be like e to the t. It would be exponential growth in the number of rabbits. However, this all depends on how hospitable the environment is for the rabbits, which depends on the number of foxes. This number here is going to be positive as long as y is less than 1. So if the number of foxes is less than 1 million, then the rabbits are still, like the rate of growth is positive. If y is more than 1, then we start to see, so x prime would be negative. So if there's too many foxes, then we start to see fewer rabbits. Meanwhile, this one is analogous to understand. This is like if this number is negative, meaning there's less than 2 million rabbits, then y prime is going to be negative. In other words, we're going to start seeing fewer foxes. Meanwhile, if we do have at least 2 million rabbits, then we'll start to see more foxes. The number of foxes will grow. Okay, so if there's more explanation of like deriving equations like this in 9.3. But I was just talking for a minute about, like, why is this a reasonable system? So if we accept that, then let's take this system and find and classify all critical points. So to find the critical points, I set both of these equal to 0. So since this is already factored, this just tells me that x equals 0 or y equals 1. This one tells me that y equals 0 or x equals 2. So, yeah, so logically, how does this work? I know that one of these things is true, and one of these things is true. So, x could be 0. If x is 0, well, and I also, one of these things has to be true. But if x is 0, then this one can't be true. So if x is 0, then this one must be true. So I've got 0, 0. So, okay, so how did I get that one? I got that one by assuming that x was 0. The other possibility is that y is 1. If y is 1, then I look down here, one of these has to be true. Well, y can't be 0 because y is already 1, so it must be this one. Yeah, so I've got 2 critical points. And in retrospect, this makes perfect sense. Let's think about, again, going back to just rabbits and foxes and talking about how these things work. 0, 0 should obviously be a critical point, because if we start with 0 rabbits and 0 foxes, we're always going to have 0 rabbits and 0 foxes. That is, it's going to stay right there. Meanwhile, 2, 1 is just like x being 2 is what makes this 0, and y being 1 makes this 0. And that's kind of a sweet spot in the sense that if you have exactly 2 million rabbits, then that's like the perfect number of rabbits where it makes the number of foxes just stay where it is. And meanwhile, you have the perfect number of foxes that are sort of eating the rabbits at the rate that keeps the rabbits where they are, and it's going to stay there forever. So the critical points that we got make perfect sense. So now let's classify them. So we classify 0, 0. I'm going to find the Jacobian matrix. And actually, whoops. Since I'm about to do partial derivatives, so let me multiply this out. This is x minus xy. And this one is xy minus 2y. That'll make my life easier. So, okay, here we go for the Jacobian. Partial derivative of this with respect to x would be 1 minus y. Partial derivative of this with respect to y would be minus x. Partial derivative of this with respect to x would just be y. And partial derivative of this with respect to y would be x minus 2. Oops. Yeah. So as I said in the last example, in general, this Jacobian is a function of x and y, but you just plug in whatever point you're dealing with. So for us right now, that's going to be 1, 0, 0, negative 2. And I'm just interested in the eigenvalues of this. So it's going to be this. This is going to be really easy because I just multiply these two. I get 1 minus lambda, negative 2 minus lambda, plus 0. And I set that equal to 0. So if I'm smart, I won't multiply anything out. I will just say lambda equals 1, or lambda equals, I guess, negative 2. So what do we have? We did have one eigenvalue that had a negative real part, but we also had a positive real part. So this is unstable. Which is probably good news for the rabbits and the foxes. Why? This is the critical point corresponding to when, like, if you start out with 0 rabbits and 0 foxes. If this were stable, that would be a bit disturbing, because that would mean that if you start out close to this point, like if you start out with just maybe a few rabbits and a few foxes, if this were a stable critical point, then we would move towards it, meaning we would move towards fewer rabbits and fewer foxes, in fact, to the point where we approach 0 rabbits and 0 foxes. So the fact that this is an unstable critical point is probably good news for the rabbits and the foxes, because that basically means that as long as we start out with a few rabbits and a few foxes, the populations aren't going to move towards 0. Meanwhile, let's classify the other critical point to 1, and I can steal some of my work because I already did like the general Jacobian. I did j of x, y, and before I was plugging in 0, 0. Now I'm just plugging in something else. But I'm just saying I can steal my answer from before. So this time I'm putting in 2 for x, 1 for y. So this one is 0. This is -2. This is 1. This is 0. Okay. And then now I'm just doing the eigenvalues of this one. So I do that. This is just lambda squared plus 2. And I solve this for lambda. Ooh. Yeah, this one is going to be, so, I'm getting ahead of myself because I just realized what's going to happen. Lambda squared would be -2, so lambda is plus or minus root 2i. So this is pure imaginary. So, yeah. I guess, yeah, unfortunately, this is the one that's inconclusive. But let me say a bit more about that. If you remember, these are almost linear systems. If this was a linear system with pure imaginary eigenvalues, then that would be indicative of like a critical point where the solutions just trace out ellipses, like it just goes around like this. But this is not linear. Yeah, this is a terrible ellipse. That's supposed to be the center, but this is not exactly linear. This is almost linear. The differential equations, like it had an xy term in it, making it non-linear. So the solution is not necessarily going to be like a perfect ellipse coming exactly back to the same point where it was. The fact that there's a little bit of error making it non-linear means that it might sort of go around, and when it comes back, it doesn't quite hit the same point. Maybe it's a little bit closer than it was, or a little bit farther away. So, right. This is, I don't know whether the rabbits and the wolves like this or dislike it, but, roughly speaking, this means that there's this point 2, 1, where, roughly speaking, if we were to ignore the nonlinearity of this, the solutions are sort of going around this point. And like I said, it might not be a perfect ellipse. It might not come back to the exact same point that it came to, but it's moving around, which is maybe disturbing for the foxes and rabbits, or maybe not. It kind of means, roughly speaking, that if you are close to this point, then you move around this point. And you can imagine how this goes. This point is like the perfect point where the rate at which the rabbits are breeding is lining up with the rate at which the foxes are eating the rabbits, so that the rabbit population is remaining stable. And meanwhile, the rabbit population is at the perfect level to sustain that exact number of foxes. Now imagine that we're close to that point. Like, maybe we have the perfect number of rabbits, but the number of foxes is just a little bit less than perfect. Whoops, maybe I should draw this going around the other way. Yeah, because I think this should move like counterclockwise around the point. So let me say this again. We have the perfect number of rabbits, because that's X, but Y, the number of foxes, is just a little bit underneath the equilibrium point. What that means is that we should start gaining more rabbits because the number of foxes is less than it should be. So X is going to increase. That's why I drew this moving counterclockwise. So X is going to increase, so we're going to move that way. Now, once we start getting more than the perfect number of rabbits, that's going to increase the number of foxes, meaning Y is going to move up. So as X moves to the right, Y moves up, until we reach a point where we start to have more than the perfect number of foxes, in which case the number of rabbits starts to go down. So when Y reaches this point, this is like the perfect number of foxes, and Y actually starts to move above that point, that's when X starts to decrease and we start to move to the left. And yeah, so maybe now you get what I'm trying to explain, that at this point we have the perfect number of rabbits again, but now we have too many foxes. Y is above where it should be. So the number of rabbits should keep going down until we have less of them, and then the foxes go down as well. And we sort of circle, roughly speaking, we circle around this point. And again, like I was saying, this is not a perfectly linear system, so we may not circle back around and hit the exact same point we were at. But roughly speaking, we're moving around this point. And that's what happens when you get pure imaginary. But everything I just said is a little bit extra. As far as answering the question goes, I would be happy with just saying inconclusive because it's pure imaginary.